Good day, everyone. I'm happy to share our research entitled An Algebraic Targeting Approach for Decarbonization Cost Calculation. My co-authors are Professor Kathleen Aviso and Professor Imantan from the De La Salle University, Philippines, and Professor Dominic Fu from the University of Nottingham, Malaysia. My name is Maria Victoria Migo Samagang. The presentation is divided into 5 parts, and we will begin with the introduction. There is undeniable scientific evidence that human-made emissions are causing global warming. The modeled pathways that emit global warming to 1.5 degrees Celsius require emissions to peak by the year 2025, which is less than 2 years from now, and to reach net zero emissions by the year 2050, according to the latest IPCC report. And without our mitigation efforts, global warming will cause severe climate impacts that will lead to billions of dollars in economic loss and will make it difficult for humans to thrive. The same report also listed strategies to counter climate change. This includes renewable energy. If fossil fuels will still be used, it should be accompanied by carbon capture and storage. We have demand-side measures, improving efficiency, and now negative emission technologies or NETs. NETs remove carbon dioxide from the atmosphere for storage in a different environmental compartment. And according to the IPCC report, NETs are now needed to counterbalance the hard-to-abate residual emissions to reach net zero, especially because we have difficult to decarbonize industries like aviation, heavy transport, etc. This figure shows the most prominent nets in the literature, and I want to highlight two nets because of their capacity to provide energy as well as negative emission. Biochar that sequesters carbon in the soil in the form of stable biochar, and bioenergy with carbon capture and storage or BECCS, where it uses carbon neutral biomass for energy and then the exhaust carbon dioxide is captured and stored. I want to emphasize that there are two motivations behind nets. One is biophysical and the other is economical. Biophysical because the conventional approaches are not enough. We are way past the point wherein we can reach net zero emissions by conventional approaches alone. Economical because immediate and full decarbonization will also be unlikely. Hence, there is a need to integrate and plan nets to decarbonize our energy systems. Process integration can help with that. Process integration consists of methods that integrate whole processes to reduce resource consumption and emissions. And this table summarizes the known techniques in carbon and footprint management and the tasks involved, which are simulation, optimization, network designing, selecting, and ranking. We have the graphical techniques like pinch analysis and marginal abatement cost curves, and we have the mathematical programming approach, the combination of graphical and mathematical approaches, which is a process graph. No technique is superior, each has its own merit. For example, graphical techniques are good visual communication tools that can provide the initial assessments and insights to decision makers, but they are tedious and limited by accuracy issues. On the other hand, mathematical programming can address the complexity and lack of detail at the expense of reduced interactivity. Here are some literature on the use of process integration techniques to decarbonization planning and nets. In general, there are few studies integrating nets in energy systems. So we have studies on using mathematical programming techniques, and we have studies using graphical techniques like the carbon emission pinch analysis or CEPAM, and we also have the marginal abatement cost curves or Mach curves. Although Mach curves is a simple but effective tool, there are very few studies using Mach curves for decarbonization planning. To address this knowledge gap, the study has two objectives. First, so these are the knowledge gaps, and the objectives are first to develop an algebraic targeting technique based on Mach curves that automatically calculates the total system cost. And second, to apply the technique or to demonstrate the technique in a case study of CO2 emitting sources and nets. This work supports the analysis of decarbonization portfolios to fight climate change. Moving on to the problem statement. Given a system of CO2 emitting sources and a system of nets, and there's given their specific costs and emissions or negative emissions for the nets, the objective of this work is to target net zero emissions and based on the Mach curve and calculate the total system cost using an algebraic approach. Moving on to the proposed methodology. But a quick background on the traditional Mach. So in traditional Mach curves, um, it shows the most cost-effective options per unit of emissions reduction. So the vertical axis shows the specific costs, and the horizontal axis shows the cumulative emissions reduction. Each of the block here represents different emission reduction options. The options are arranged in increasing Mach or increasing specific costs. So to get the total cost, the areas of the blocks have to be added manually, which is tedious to do. And our team published a paper on graphical net zero emissions planning based on the Mach curve. So it involves plotting the CO2 emitting sources cumulatively in increasing specific costs and then plotting the negative emissions in increasing specific costs but in the opposite direction. So the gap between the last negative emission technology and the vertical axis gives the net zero deficit or the additional amount of negative emissions required to reach net zero. So this is the net zero deficit. But for this paper, we are presenting this algebraic approach to targeting net zero emissions and calculating the total cost based on the previous graphical Mach curve. It starts off with the construction of the basic structure or the cascade table. For the detailed steps, please refer to the one-page abstract. But I want to highlight two things. So the first is the net zero deficit, which I mentioned earlier, the additional negative emissions required to reach net zero, is automatically determined by this table, by constructing this table. And also, the total system cost is also automatically calculated by constructing this table. So please refer to the one-page abstract. And then after constructing the table, we move on to the algebraic targeting steps. To target net zero emissions, we can add the net zero deficit. We add the net zero deficit to any values in the nets column. So this action increases the negative emissions of the system. And also it updates the total cost. Alternatively, we can also subtract the net zero deficit to any of the values in the CO2 emitting column. This is the CO2 emitting column, and this action decreases the emissions in the system. So to illustrate this procedure, let's move on to the case study. So this is the case study data. The system consists of two CO2 emitting sources, the coal and natural gas power plants, and we also have two nets, the BioChar and BECCS. And here is the data on their specific costs and emissions. A negative sign here means negative emissions, and that is for the nets. So following the steps in the basic structure table, okay, so after constructing that, we have the baseline scenario. And here we can see that there's a net zero deficit equal to 1.59 megatons of carbon dioxide. So this is the net zero deficit or the additional negative emissions required to reach net zero emissions. And we can also see that the baseline total system cost is 398 million US dollars. So if we want to target net zero emissions by increasing the capacity of BECCS, we have to add this amount to the BECCS capacity. And by doing that, it updates our system. So now our BECCS has this capacity 4.58 from 2.99 megatons of carbon dioxide. And notice that our net zero deficit is now zero. So um, it automatically updates our table, but it also gives us the updated total system cost, which is now more expensive. It's now 557 million US dollars from 398. Another option is to decrease the whole capacity or any CO2 emitting source. But for this example, let's decrease the coal capacity by 1.59. And we do that by subtracting this amount from the whole capacity. So we do that and it updates our system from the initial 4.14 coal capacity to 2.55 megatons of carbon dioxide of emissions from the coal power plant. And the net zero deficit is zero. Our total system cost is cheaper. It's now 382. So it shows that it's cheaper to reduce the CO2 emitting source than add nets for this case study. Comparing the results of the algebraic technique with the graphical technique yields the same results. But in the graphical technique, all of these steps are done manually by shifting the graph. And the total system costs are manually calculated by hand by getting the areas under the curve, which is tedious. So in conclusion, this study met two objectives. The first is an algebraic approach based on the map curves was developed. It allows for algebraic net zero emissions targeting and the automatic total system cost calculation. Second, the technique was applied in a case study on nets and fossil fuel power plants. This work supports the analysis of decarbonization portfolios to fight climate change. For future work, the cost calculation of renewable energy sources can be integrated in the technique. We have now reached the end of the presentation. Comments and questions are welcome, or you may also email me at this email address. Thank you very much.